So hello everyone, a very good afternoon to everyone. Today in this session we are going to see the topics of power system, that is system stability concept and equal area criterion. So in the last session some of you were asking about the standard textbook that you may follow. So I would recommend these following textbooks and you can follow that. So first textbook I would recommend is that Power System Engineering by DP Kothari and IJ Nagarath. And second textbook you may follow Power System Analysis by John J. Granger and William D. Stevenson. This book is very standard book and very basic book. Second one. And and the NPTEL course you may follow Power System Analysis by Professor Devapriya Das, IIT Kharagpur. Whatever the book you want to follow, any of them you can refer. And one of the advanced book that I was telling in the last class, that is Power System Stability and Control. Stability and Control by Prabha Kundur. So any of the textbooks you follow and just you solve the problems and practice the problem. So let us begin today's session. So today we are going to see the concept of power system stability and we will solve the problems based on that. So we will take a quick recap on the expressions that we will needed to solve the problems. So first is that inertia constants and swing equation. So we all know that the relation between degree and mechanical degree. So electrical degree is always greater or equal to mechanical degree. So you can write theta E is equal to P divided by 2 into theta mechanical. And here P is the number of poles of machine. So this is very basic and we will use this expression. Now we will see that rotor kinetic energy at synchronous speed. So for that expression is kinetic energy, we can write half of J into omega sm square into 10 to the power minus 6 megajoule. So here J is the moment of inertia of rotor and it is given in kg meter square. So always also just take care of the units also. And omega sm is the synchronous speed in mechanical radian per second. Now we will use this relation of electrical degree and mechanical degree. So we can write omega sm is equal to 2 divided by P into omega AC. And on putting this value, we can see that we take 1 omega AC inside this full bracket and omega AC outside this bracket. So you can write kinetic energy is equal to half m omega AC. So this is another way to express the kinetic energy, where one way to write it in J term, that is moment of inertia in kg meter square, and one way is to write in m form, where m is in the moment of inertia in millijoule second per electrical radian.
So I think J is inertia constant and M is moment of inertia.
No, this is a moment of inertia. Inertia constant, we will see. This is correct one. This is correct. Don't confuse here. So now we will define the inertia constant as such that we can write G into H is equal to half of m omega AC. Both are equal to kinetic energy, and where G is the 3-phase MVA rating of machine, and H is the inertia constant, and the unit for inertia constant is millijoule per MVA or megawatt second per MVA or second. So all these units, there are different ways to write the units for inertia constant. So you can use any one of them, and we can also see in the options that they may write in it in millijoule per MV or megawatt second per MV, or simply just use the second. Now we will see the swing equation, that is, we know that swing equation represents the dynamics of rotor for a synchronous machine. So for swing equations we can write input power minus output power, that is PM. We represent here mechanical power, that is initial electrical power, and minus P the electrical power output. So it is equal to GH divided by 180 degree F into d square delta dt square, where delta is the rotor angle. So you can write it also m into alpha. So where alpha is the rotor acceleration in electrical degree per second square. Now if you write it in per unit form, then you have to divide with the system base. So on dividing both sides by G, and that is also we have seen that this is 3-phase MVA rating or system base of the machine. So we will get the swing equation in per unit form. So PM minus PE is equal to H divided by 180 degree F into d square delta divided by dt square. So this is the accelerating power. Left hand side is the accelerating power, that is mechanical power minus electrical power, is equal to m per unit into alpha, and where m is represented as h divided by 180 degree into f. Now next we will see that how we will find the equivalent inertia constants if we are having the different machines present in the system, like we are having multi machine system. So how we can find the equivalent inertia constant, and we have taken the assumption that all the machines running in the cohesion means, uh, running coherently means, that is they are swinging in unison. That means that all the rotor angles are equal. So delta 1 is equal to delta 2, we can assume it as delta. So for this type of system we can write that equivalent inertia constants taking top by taking the ratio of total kinetic energy to the system base. So total kinetic energy will be G1 H1 plus G2 H2 plus so on, all the machines present in the system. So we can find the equivalent inertia constant for multi machine system, like taking the ratio of total kinetic energy divided by the system base. So here G base is the common system base. Now you may have seen the questions where it is it has been asked about the natural frequency of oscillation. So in that type of problem, we will use this expression omega n is equal to under root of partial derivative of Pe with respect to delta at delta is equal to delta naught initial rotor angle divided by m, and that will give in radian per second. And in the question, if it is asked in hertz, then you use this divide omega n by 2 pi, so you will get the answer in hertz. And here m, you have to put this expression m per unit will be h divided by pi f, because this the unit is radian per second. Next is that critical clearing angle and critical clearing time. So what is the critical clearing angle? It is the angle at which the fault must be cleared so that the system is to remain stable, and that equal area Criterion is to be satisfied. So here is the P delta curve, and Pm is the mechanical power and initial rotor angle. And suppose if fault occurs at this time, so the after that the electrical power becomes zero, and it should must be cleared before this angle delta Cr, so that system remain stable. If the fault clears after this angle delta Cr, then the system becomes unstable. So this is delta Cr. And how we can find this critical rotor angle delta Cr? By using this equal area criteria. So applying equal area criterion, here we will get this expression delta Cr is equal to cos inverse pi minus 2 delta naught into sine delta naught minus cos delta naught. If you want to remember this expression, then you can memorize it, but if you just you solve this expression, then you also get this formula. And corresponding to delta Cr, we will get the critical clearing time, and this is expressed as under root of 2h delta Cr minus delta naught divided by pi f Pm. So these are all
Sir,
this.
I am having one doubt.
Yes.
So, what is the fault occurs after delta is critical clearing angle is attained? Before it's a fault occurs before, then it is means given that delta CR should be attained to the fault not occur. I guess you are saying.
This is for single machine connected to infinite bus system. So there are different chances like that. If there is parallel, if there is parallel 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 lines connected between connected between the generator and to the load side to the infinite bus, then there is different scenario. I have taken this single machine system connected to the infinite bus, so that's why I made this figure. This critical clearing angle is applicable to this case only. There may be different cases, but one thing here means fault occurs at this means like they are running in synchronous, they are running at a steady state by at this angle delta naught. So if the fault occurs, then electrical electrical power will become zero. So this should must be cleared before delta Cr, before this reaching this critical clearing time, so you will not get so that system will remain stable. Okay.
सर एक क्वेश्चन पूछना चाहिए कि डेल्टा सीआर अटेन करने के बाद भी फॉल्ट आ सकता है क्या?
After delta Cr,
यस सर, अगर अटेन कर लिया होगा तो भी फॉल्ट आ सकता है।
no means if they remove the faults, if they remove the fault, then the system will again run at this delta naught. Understood? Means like,
ओके, ओके,
means if you see the system, I will make the system, if you take the example of one system that is a single machine system connected to the infinite bus system, then this situation happens. Then
ओके सर।
So let us see the problems for today's session. So first problem is that a 500 megawatt 21 kV 50 Hertz 3-phase 2-pole synchronous generator having a rated power factor of 0.9 and has a moment of inertia of 27.5 into 10 power 3 kg meter square. So the inertia constant H will be, and the options are 2.44 second, 2.71 second, C option is 4.88 second, and D option is 5.42 second. So all of you try yourself also, and if you face problem then you can see here how I am solving. And whoever is getting answer, type your answer in chat box, and also you can tell. So, so first we will find here G, that is machine rating in MVA. Machine rating in MVA, we will get it by P divided by power factor. P is given as 500 megawatt and power factor is given as 0.9. So this will come out as 555.56 MVA. So we know that kinetic energy is half of J omega Sm square. So we can write this in omega AC term also. So half of J into 2 divided by P square omega AC. This will give you in the terms of joule because we have not multiplied with 10 to the power minus 6. So this will be half of 27500 into 2 divided by 2 whole square omega AC, that is 2 pi into 50 square. So multiply with 10 to the power minus 6, that will give into the kinetic energy in megajoule. So here you will get 1357.07 megajoule, and so we can write H is equal to kinetic energy divided by G. So 1357.07 divided by 555.56 megajoule per MVA. So this will give you 2.44 megajoule per MVA. So the correct answer for this is A. How many of you get this answer A? No one replied yes. Biraya replied 2.44 second. Correct. So if you use this expression omega sm, then you have to write omega sm as 2 pi ns. So this is little bit older problem and has been asked in GATE 2009 2 marks. So someone wants to use omega sm, then you can use that way also. So omega sm will be 2 pi ns, so that will give you mechanical radian per second, and omega AC is electrical radian per second, that is 2 pi f. Since here this is two pole system, two pole synchronous generator, then both omega sm and omega AC will be equal to 100 pi. And ns is equal to what? Ns is equal to 2f divided by p, that is rps. So whatever the way, you have just be clear about that. So you can write ns is equal to 120 f divided by p, that will give you the rpm. So on putting all these terms here, you will get 3000 rpm, and ns you will get ns divided by 60, so this will be 50 revolution per second. So these things should be clear, so that's why I have noted down here. So now let us move to the next problem. So the next problem is that a 20 MVA 11.2 kV 4 pole 50 Hz alternator has an inertia constant of 15 megajoule per MVA if the input and output powers of the alternator are 15 megawatt and 10 megawatt respectively. The angular acceleration in mechanical degree per second square is. So this problem has been asked in GATE 2022. This is recent problem. So this has been asked in GATE 2022. Whoever is getting answer, you can type your answer in the chat box. And if you have any doubt while solving the problem, you can ask. So for solving this type of problem, we will use the swing equation. So what are the things we have been given? So given our system machine base, so that is 20 MVA, and then we are given with input power P in is given with 15 megawatt, and output power is given as 10 megawatt, and that's all. So we can use the swing equation. Swing equation, we know that Pm minus Pe is equal to Gh divided by 180 degree F into d square delta divided by dt square. So here the angular acceleration has been asked, so that is d square delta divided by dt square. So we will get Pm minus Pe, that is we get 5 megawatt, and here G is given as 20 MVA, and BR H H is given as H is also given, so H is given as 15 megajoule per MVA. So H is given as 15 divided by 180 degree into F. So this is the angular acceleration. We can represent it as alpha. So okay, wait, 75. Nagula has got the answer. Very good. 75. So we can write here this, and F is also we can write. So alpha will become as 150.
150, 150,
Is correct.
150.
150 electrical degree per second square. So in this question it is asked about mechanical degree per second square. So you know that theta m is equal to 2 divided by p theta electrical. So you can write alpha is equal to 2 divided by p into 150 electrical, sorry, mechanical degree per second square. So p is given as 4. So it on substituting p is equal to 4, then you will get 75 mechanical degree per second square. So the answer will be 75. So this is very important string equation. You can use the actual form also, and you can use the per unit form also. Both from both form we will get the same answer. So now we will see the next problem. So the next problem is that this figure shows the single line diagram of a power system with a double circuit transmission line. The expression for electrical power is 1.5 sine delta, where delta is the rotor angle. The system is operating at the stable equilibrium point with mechanical power equal to 1 per unit. If one of the transmission line circuits is removed, the maximum value of delta as the rotor swings is 1.221 radian. So if the expression for electrical power with one transmission line circuit removed is P max sine delta, the value of P max in per unit will be. So this is very good problem. So yes. So first we will make the power delta curve. So how this power delta curve looks like? So before fault occurs, means before when when both the lines are present, then you can make the P delta curve like this. So this is P max 1, and it will be given as the expression for delta electrical power is 1.5 sine delta. So this expression is given as 1.5 sine delta. So P max 1 will be 1.5 per unit. Now when one of the line is removed, then this curve will be get down. Suppose this looks like this. So this will be P max 2, P max 2. Oh God, P max 2. We have to find this P max 2 value. This is unknown. So we will find this P max 2. So this machine is stable at this rotor angle. It is running at a steady state at this value. So this is the initial rotor angle. When both the lines are present, the system is running at this rotor angle. We have to find this initial rotor angle also. So we can write initial rotor angle, that is Pm. So we can write Pm is equal to P max 1 sine delta naught, and Pm be is equal to 1 per unit. So where it is given, we can see that mechanical power equal to 1 per unit. So this will 1 per unit, and P max is 1 is given as 1.5 sine delta naught. So from here you will get delta naught as 41.81 degree or 0.73 radian. So delta naught will 141.81 degree or 0.73 radian. Now the next, we can see that the steady state point after this one line is removed, then it is stable at this angle delta 1, because this mechanical power should be equal to electrical power for a steady state operating point. And suppose this rotor swings to the maximum value at delta 2, and delta 2 is given by this. Here it is written that if one of the transmission line remove the maximum value of delta where the rotor swings is 1.221 radian. So delta 2 is given as 1.221 radian, and this is equal to 69.96 degree. So for the system to be stable, both the energy, both the this area will be equal. Suppose this area is A1 and this area is A2. So here we will apply the equal area criterion. So using equal area criterion, A1 is equal to A2. So we can, for A1, it is going from delta naught to delta 1, that is final operating point. Delta 1 is the final operating point. So this area will be Pm minus P max 2 sine delta d delta, and the maximum its rotor swing set delta 2, and this final operating point is delta 1. So this will be p max 2 sine delta minus pm d delta. So you solve pm, sorry, so pm will come out. So here delta delta 1 to delta naught minus this cos delta, integration of cos delta is, integration of sin delta is minus cos delta, so it will be plus p max. So cos delta delta naught to delta 1, and again here p max to cos delta delta 2 to delta 1 minus pm delta from delta 2 to delta from delta 1 to delta 2. So we take common, pm will be delta 1 minus delta naught. So take this side pm delta, so it will be delta 2 minus delta 1, and this will become minus of p max 2 cos delta 2 minus cos delta 1 plus cos delta 1 minus cos delta 1. So on removing the delta 1, we will get p max 2 pm delta 2 minus delta naught divided by cos delta naught cos delta 2. Till here, is there any doubt? So now we'll put all these values. Now we will put all these values. We will get p max 2. P max 2 is pm delta 2 minus delta naught divided by cos delta naught minus cos delta 2. So pm is 1 per unit, delta 2 is 1.221 minus 0.73 divided by cos delta 1, cos 41.81 degree minus cos delta 2 is 69.96 degree. So it will be 0.4913 divided by 0.4026. So it will become as 1.220 per unit. So the final answer for this problem is 1.22 per unit. So is there any doubt in this problem? Sorry, sorry guys. So there is in my side here too much rain is happening. So sorry for the trouble. Share a screen, change share a screen. So entire screen. Antanu, can you see the screen?
No, sir,
A screen is not visible.
not visible.
Now,
Now, now okay.
okay, fine.
Yes, sir, visible.
Yes, okay. Thanks. In Guwahati side, today so much rain from the last 2 hours, raining is going on. So, so is there any problem in this question number three? Any doubt? Any clarification? So you have to just apply the equal area criterion and you will get the answer. Now we will see the next problem, that is question number 4. So this problem is that a cylindrical rotor generator delivers 0.5 per unit power in the steady state to an infinite bus through a transmission line of reactance 0.5 per unit. The generator no load voltage is 1.5 per unit and the infinite bus voltage is 1 per unit. The inertia constant of generator is 5 megawatt second per MVA and the generator reactance is 1 per unit. The critical clearing angle in degrees for a three-phase dead short circuit fault at the generator terminal is. Anyone want to speak? So if there is no doubt, then you can just mute yourself.
What was the answer for the next previous question, sir?
1.22 per unit.
What was my answer? 2.21. Maybe some mistake.
So, you can check your answer later. But right now you solve this problem. Question number 4. So here in this problem, we are given one generator that no load voltage is 1.5 per unit, and this no load voltage is 1.5 per unit and infinite bus voltage 1 per unit, and transmission line reactance is given as, and the generator reactance is given as 1 per unit, and this transmission line reactance is given as 0.5 per unit. So a cylindrical rotor generator delivers 0.5 per unit. So this is connected to infinite bus, and this magnitude is how much? An infinite bus voltage is 1 per unit. So V is given as 1 per unit. So here we will find this first initial angle. Electrical power is equal to P max 1 sine delta naught. So electrical power it is given as 0.5 per unit, so it is delivering 0.5 per unit power. So it's better to write pm, so that you don't confuse. Pm is 0.5 per unit, that is equal to initial electrical angle, and p max 1, how we can find? Mod d mod v divided by x equivalent sine delta naught. So 0.5 mod e 1.5 1, x is 1 plus 1.0.5, so delta naught will be 30 degree or pi divided by 6 radian. So this is the initial rotor angle. Now we will make the curve p delta curve. So initial rotor angle is at pm, that is pe naught is given as 0.5 per unit, so delta naught is given as 30 degree, and fault occurs at this side, so it is uh, clear at critical time. So you can say that this delta c, and this becomes delta m, and delta m equal to what? Pi minus delta naught. So this should be equal to this area, so we can write it as a1 and a2. So applying equal area criterion, applying equal area criterion, area a1 is equal to area a2, so this will become pm into delta c minus delta naught. This is just the rectangle, and taking the integration from delta c to delta 1, that is delta m, delta c to delta m. So delta c to delta m, pe minus pm d delta. So here we can write pe del c minus del naught is equal to p max. So pe is equal to p max sine delta. So taking integration of sine delta will be minus cos delta, so it is del c to del m, and minus pm pi minus delta naught, and also we know that delta m is equal to pi minus delta naught, pi minus delta naught minus delta c. So take this pm one side, initial power, initial electrical power, so delta c minus delta naught plus pi minus delta naught minus delta c is equal to p max cos delta c minus cos pi minus delta naught. So this will be pm pi minus 2 delta naught, this becomes p max cos delta c. Cos pi minus delta naught will be minus cos delta naught, so it will be plus cos delta naught. So from here we can write cos delta c will be pm pi minus 2 delta naught divided by p max minus cos delta naught. This will be 0.5 pi minus 2 divided pi by 6 divided by 1 minus cos pi divided by 6. So this will be cos del 6 0.5 into 2 pi by 3 minus cos of pi by 6 is root 3 by 2. So we will get cos of delta c is equal to pi by 3 minus root 3 by 2 is equal to 0.118, sorry, 0.18 radian, 0.1812 radian, and in degree it will be 79.562 degree. So you can also write cos delta c is equal to 79.6 degree. So from the options it is nearly equal to 79.6 degree. So the correct answer for this problem is 79.6 degree. D option is correct. So here you can apply that expression also that we have seen in the starting. This expression, as you were telling, this critical clearing angle cos inverse pi minus 2 delta naught sin delta naught minus cos delta naught. The same expression you can apply in the question number 4, and this is asked in GATE 2012, 2 marks problem. So now we are going to see the last problem of today's session. So this problem is says that a synchronous generator of reactance 0.40 per unit is connected to an infinite busbar. Magnitude is 1.0 per unit through transformers and line of total reactance of 0.20 per unit. The generator no load voltage is 1.20 per unit and its inertia constant is h is equal to 5 seconds. The resistance and machine damping may be assumed negligible. The system frequency is 60 Hz. Calculate the frequency of natural oscillation in Hz if the generator is loaded at to 60% of its maximum power transfer limit. In this problem here you take it as P max. So in this problem it is given that one generator is connected to an infinite bus. So this is generator having no load voltage is 1.20 per unit, and the reactance of generator is given as J 0.40 per unit, and the line reactance is given at J 0.20 per unit. It is connected to infinite bus. So magnitude of infinite bus will be 1.0 per unit is given. So here we know that natural frequency of oscillation, we have seen the expression for natural frequency of oscillation. Natural frequency of oscillations del Pe divided by partial derivative of electrical power at delta naught divided by m. We take under root of whole omega n. So this is we have seen in the starting slides. So now we will apply this one. So here we can see that generator loaded at 60% of maximum power transfer limit. From this we will find the we will find the P maximum value, electrical value. So we can write electrical power is equal to 0.6 of P max. So we know that P max electrical power is also equal to P max into sine delta naught. So from here we will get sine delta naught is equal to 0.6 and cos delta naught we will take 1 minus 0.6 whole square, that will be 0.8. Now we will find the P maximum value. How can we can find mod D mod V divided by X? Mod E is given as 1.2 and mod V is given 1 and X is given at 0.6, so it will be 2 per unit. So we get PE expression as 2 sine delta naught. So we will take the derivative of delta PE, delta partial derivative of active electrical power. It will be 2 of cos delta naught, 2 of cos delta. Here delta will not come, and this del PE at delta is equal to delta naught will be 2 cos. We have found out this cos delta naught. Cos delta naught is 0.8. So just substituting cos delta naught 0.8, you will get 1.6. This we got. Now we will find m per unit, h divided by pi f. So what is the value of h? H is given as 5 second. So 5 second divided by pi into frequency is given as 60 hertz frequency is given, so it will be 5 divided by 60 pi. Therefore we will finally be put all these value in omega n, so we are getting del p divided by del naught is equal to 1.6 and m value is we are getting 5 divided by 60 pi. So we put all, we simplify this, then you will get 7.7665 radian per second. Therefore frequency in hertz will be omega n divided by 2 pi. So it will be 7.7665 divided by 2 pi is equal to 1.236 hertz. So answer for this problem is 1.236 hertz. So is there any doubt till here? Sanchi, Ritesh, Antanu, Saurabh, Anil.
No, sir, everything is clear.
Only one doubt: when to use omega as 2 pi f, and when to use it as in terms of synchronous speed.
When you are finding with mechanical radian, then you have to use 2 pi ns. Otherwise, when you are finding the electrical radian per second, then you have to use 2 pi f. So as I shown this first problem itself. So omega sm is 2 pi ns and omega ac is 2 pi f. So this is common mistakes people are doing. So that's why I have noted down here. And ns you know how to find. ns is rps. That
2
means
f by p. 2 f by p.
yes, revolution per second. So just take care of this thing. Like if you are adding kinetic energy in mechanical radian per second, then you have to put this value. And if you have found the omega ac, then you have to convert this expression in this form. Either way, you will get the same answer. This is a very silly mistake people are doing. Okay, Antanu. Other,
Sir,
yes.
sir, I would like to ask if we are giving a phase sequence RYV, then how is if we are giving a diagram in which we have provide three line voltages. So if we are asked to find the phase sequence of the RYV, then how do we know the angle of this particular phase voltage or line voltage diagram?
Means in the problem it is always said that it is balanced or unbalanced system. It balanced system is given, then you have
Yes, a balance. Three-phase. It was asked in GIT 2021. A three-phase balance voltage is applied to the load shown. The phase sequence is R by V, the ratio of IV by IR. So, in this question, the ratio of mod of IB by IR is asked, but for that we have to find the angles. So, how do we know how to find that?
You can send in the group, that NPTEL group. You can send. Many are there. They can solve.
yeah. Because
Okay.
if I don't means if I have because I am not knowing the question, that is the problem. If I knowing the diagram, then I will express. And you can, if you have any problem, then you can ask me in the doubt also. Means to through this more mail. You can tell me personally, then I will solve in the next session.
You have to name.
This mail sahilgaurav@iitg.ac.in. I will just uh, solve that problem so that everything is clear. Mm,
Okay, sir. Thank you, sir.
yes, sure. So, okay, all right. Thank you for joining the session, and we will meet on the next Saturday at the same time. Thank you, everyone.